Comparison of proportions is quite common in the medical field where you're comparing a treatment to a placebo and you've got data for the percentage of people who have improved in one treatment or another, and you want to compare if those differences are significant or not. So in this screencast, I'm going to talk to you about how we can compare population proportions or binomial proportions. The example we're going to be working through, your friend claims that she can pick good cantaloupes more often than you. You assemble a panel of close friends and have a cantaloupe pick-athlon during an early fall weekend. Out of 107 cantaloupes that your friend picks, 85 of them are good, so that's a population proportion. Out of 79 cantaloupes that you pick, 55 are good. Can she claim with at least 95% confidence that she picks cantaloupes better than you? So let's talk about how we can compare two population proportions. This is for large sample tests, so we have to convert this to a normal distribution approximation. N times P must be greater than 5 for each of the two populations, and N times 1 minus P has to be greater than or equal to 5 for each of the population proportions. So keep that in mind. This is large sample tests. We have two samples of different sizes, N1 and N2. The random variables x1 and x2 represent the number of observations passing a certain criterion. For example, in our cantaloupe example, this would be the successes or the good cantaloupes. Assuming that the normal approximation to the binomial is okay, we can calculate our proportions of successes, x1 over n1 and x2 over n2, and we assume that those are both normally distributed because we've got a large sample size. The hypotheses, we can have a two-tailed test, a lower-tailed test, or an upper-tailed test. For all of these tests, we calculate a test statistic. Shown here, we want to look at the difference in population proportions and compare that to a hypothesized difference. And a lot of times, the difference is going to be 0. P1 equals P2 if that's our null hypothesis. We can rearrange this a little bit, and we can calculate a test statistic, Z0. Z0 is P1 hat. Whenever we have a hat, that's our experimental observation, so we can calculate our P hat, where P1 hat is equal to x1 divided by n1, and similarly for P2 hat, we have a lumped proportion, P hat, that's just the total number of successes out of the total number of trials. So it's sort of like a overall success rate. In order to accept the alternate hypothesis and reject the null, the rejection criteria here is for the null hypothesis. Our test statistic has to be greater than z alpha over 2 or less than negative z alpha over 2. For a two-tailed test, for an upper-tailed test, our test statistic has to be greater than z alpha, so way up in the tail. And for a lower-tailed test, our test statistic must be less than z alpha. So let's go back to our example here, and let's perform this hypothesis test in Excel. We have our friends' data here, 85 successes out of 107 cantaloupes or trials. You have 55 out of 79. We can calculate the probability or the estimate for P1 hat, and that's equal to x1 divided by n1. We can do the same thing for your sample data, x2 divided by n2. Based upon the observations, this would be an upper-tailed test. We would say that sample 1, your friend, has a greater probability of success than sample 2, or you. So this is going to be an upper-tailed test for our alternate hypothesis. We can calculate our overall p hat using this formula over here, and that's just equal to x1 plus x2 divided by n1 plus n2. It's just an overall success rate, 75%. We can calculate our test statistic using this equation over here, equals P1 hat minus P2 hat divided by the square root of P hat times 1 minus P hat times 1 divided by N1 plus 1 divided by N2. And when we do that, we get a test statistic of 1.53. Just like all other hypothesis tests, we compare our test statistic with a critical value. Here we're basing this on a standard normal distribution. We can use the norm.s.inv function. This is a right-tailed test, so we have to do 1 minus alpha, or 95% to the left of it. and that's 1.645. Our conclusion then, because we have not exceeded that critical value at which we would accept the alternate hypothesis, we can claim that there's no evidence that your friend can pick cantaloupes better than you can. Hopefully this screencast gives you a better idea of how you can compare large sample population proportions. Thanks for watching.